This one is C11H14O2. It has 5 double bond equivalents. We have a 5H over here in the aromatic region. That's going to be C6H5. We have a 1H over here. That's going to be a CH. Over here we've got a CH2 and then two CH3 groups. What we have left is C, two O's and a double bond equivalent, C double bond O, and an O. Everything counts down to 0. These should be the correct pieces. Now we can see what might be connected together here, and you can look at this, the 1H here, the CH, and you can see it's got 6 peaks. That would indicate that it is adjacent to 5 hydrogens. Generally this indicates a CH3 directly connected to a CH along with a CH2. That would be 5 hydrogens adjacent to give 6 peaks. This is going to involve a C double bond O and an O, and that means that we are often looking at an ester grouping. When we look at ester groupings, there are certain things that we can predict. When we've got this situation here where we have a CH2 directly connected to an oxygen, you can see it's going to be at around 4 ppm, whereas the CH3 that's connected to the C double bond O will be between 2 and 2.5 ppm. If we apply this thinking to the example I have over here, what that would mean is that we've got this CH group at 4 ppm, indicating that it is directly connected to the oxygen. The other things we can talk about then are where the C double bond O goes and where the CH3 goes. We can get another clue about where the C double bond O is going by looking at the peak grouping in the aromatic region. What we notice is that when we have a C double bond O directly connected to the aromatic ring, that tends to split the aromatic ring into 2 groups of peaks, usually centered somewhere around 7.5 ppm. That's the situation that we have over here with our grouping. That would tell me that we do have the C double bond O directly connected to the aromatic ring. So this would be the correct structure. That would leave the CH3 down here. So now we can check on this and make sure that it does match up with what we expect. As I said earlier, the CH is around 4 ppm. We expect that's connected to the single bonded oxygen. It has a CH3 and a CH2 adjacent to it to explain the 6 peaks. We have a CH2 over here that has 5 peaks. That CH2 would be this one here. 5 peaks because it's adjacent to 4 hydrogens. This one and these 3 over here for a total of 4. We have a CH3 over here that has 3 peaks, so that CH3 must be adjacent to the CH2. The other possibility that one might have come up with for this structure might have involved something like this. But I want to point out why that would not be a correct structure. Yes, we do have the CH next to the oxygen, but look how many peaks the CH would have if this were the case. This CH then would have 4 peaks because it's adjacent to 3 hydrogens, and we have 6 peaks over here. So this kind of structure is not going to work out. So we're left with the one we came up with originally. That should be correct.